to go over the extra credit problem before we start talking about the course material proper. So I put up a web page with the 5 calculations, and I'll post it to our discussion board so that you can find it. But if you wanted to look for it from my homepage, it's preprints with a capital P and then acrostic veto 09.htm. So some of this is just to make this a self-contained document on the web. This is how some academics amuse themselves, right? You take something silly like this and turn it into a document, right? So we have the preamble, and there are actually now that there have been, let me open this in another, so this is from the Miami Herald, and Stephen Devlin, chair of the math department at USF, told the San Francisco Weekly that the chance that the numbers would come out, the letters would come out that way, are 1 in 10 million. So, okay, that's a number, but behind that number are some assumptions, and we saw last time that you make different assumptions, you get different numbers out the end. And in fact, the range of numbers that you get out of the 5 approaches that we've been talking about are more than 100 billion. So it's an enormous range of numbers depending on the assumptions you're going to make, you're willing to make, and none of them is really particularly compelling from my point of view. So we talked last time about the chance that you would get the letters in that order if basically what was going on was monkeys banging on typewriters. And that's kind of the number that it looks like he computed, 126 to the 7th power. Then we talked about what would happen if you took into account the fact that these words are in English, and that we're looking at the initial letters of words in English. So if you thought that words were drawn at random from the Gutenberg corpus, you would get an even smaller number, so 1 in 486 billion, rather than 1 in about 8 billion. So that's a rather big factor. Then we talked about the fact that suppose we let the governor keep his words and keep his sentences, but simply shuffled the lines, the 7 lines, then that gives us a number that's only 1 in 2,500. And then we get to what the extra credit assignment was. So the idea of the first part of the extra credit assignment was that you let the governor keep his words, but not the order of the words. And it's as if you wrote each of the words in those 7 lines on a piece of paper, shuffled those 85 pieces of paper together, and started drawing slips of paper and let that comprise the message. So after the 14th word, I guess you put in a line break. After the 29th word, it's after the 16th word you put in a line break. After the 29th, you put in another line break, et cetera. So you keep the line breaks where they are, but you draw the words out of a hat in a random order. If you're doing that, then in order to get the acrostic, what matters is what's the first letter of the first word on each line, and you need to know how many letters have that first word. There were how many words have that first letter? There were 8 words that started with the letter C, 3 started with F, only 1 started with K, etc. So what do you need to do? Well, you could imagine starting by picking the first letter, the first word of the first line, then the first word of the second line, et cetera, on down to the first word of the 7th line, and then let the other words kind of fall where they are. So how many ways are there to pick the first word of the first line so that it starts with an F? You have 3 choices, right? Then for each of those 3 choices, you have how many choices left for how to get a U as the first letter of the first word on the second line? 2, because there's 2 words that start with the letter U. And for each of those, you have 7 choices, right? For I'm sorry, did I say F was 3? You have 8 choices for which word starts the 3rd line to give you the C, etc. Having picked the first words of, okay, so the only one that's kind of confusing is U, because U occurs twice in the acrostic. So you have two choices for which one comes at the beginning of the second line, and then having done that, there's only one choice left for which one comes at the beginning of the seventh line. There's no more choices you can make, right? You're out of U's. So having specified what the first letters are of the first words of the 7 lines, there's 78 words left. They can be in any order in the remaining 78 places. And by assumption, when you're drawing the words out of a hat, there's 85 factorial different sequences in which you could get those slips of paper. Now, some people worried about the fact that some of these sequences aren't distinguishable from each other, that because there are some words that are repeated. If you took that into account on both ends of the problem, I would have given you credit, but nobody did. Some people worried about the fact that unnecessary was the word that occurred twice that started with the letter U, but they didn't worry about the fact that then this needs to be adjusted as well. So nobody found themselves in quite that situation. And the last one, I was really pleased with the number of people who got the last approach right. So the idea here is we keep the words in the order in which they actually occur in the message, but we throw in carriage returns at random in such a way as to end up with 7 lines, none of which is blank. So each line has to have at least one word. So how many ways are there of inserting 6 line breaks in such a way that you end up with 7 lines? Well, you can't put a line break before the first word, because then you'd have a blank line. But you could put a line break before the second word, third, fourth, on up to before the 85th word. So there's 84 places you can put line breaks. From those 84 places, you need to pick 6 in order to end up with 7 lines after you do it. And the assumption that I asked you to make was that all ways of doing that were equally likely. So there are 84 choose 6 equally likely ways to break this thing into lines. Then it's just a question of counting how many of those result in having the initial letters right. And so there, some people came really close but didn't count correctly. There's 12 ways in all, and what that's coming from, so you're stuck with the F. You're actually stuck with the U, but now what do you have as choices for the C? It could be this, or this. So there's 3 choices for the C, right? Then there's only one choice for the K. Then what about the Y? There's 1, 2 that work. Yes. And then for the O, you have 1, 2 choices for that, and there's only 1 for the U. So there's 3 times 2 times 2 is 12 possible ways that you keep the words in the same order but get them starting with the same letters as the acrostic. So the probability of this would be 12 over 84 choose 6, which is about 1 in 33 million. So I mean, this is partly just amusement, but it's also partly to get you to think about what happens when you see somebody quoting the odds of something in the newspaper. That we managed to get numbers that ranged from 1 in 2,500 to 1 in 487 billion, right? By just making slightly different assumptions. Which assumption is right? Well, I don't know. It's all concocted. It's all made up. Nobody really thinks that anybody types a veto letter by choosing words at random from the Gutenberg corpus, right? I mean, that's not, it's sort of not a realistic way to do this. So what I think these numbers speak to is that it'd be kind of hard for that to happen accidentally, but exactly how to put a number on that is a very it's very difficult to do it in a reasonable way, and you can get pretty much any answer you want. I think you'd have to tell a pretty concocted story to get the number up to, say, 10%. I don't know what, but to get the number up to 1%, probably do that pretty easily. Questions about this? So if you go online to check your homework scores, you will have, and you submitted the extra credit, you will have a score for extra 1, which is your number of points, which range from 0 to 3. I don't know, half a dozen or so people got 3 points on it. I think the smallest non-zero credit that I gave was half a point. Some people didn't get any, alas. Questions? Yeah.
Is this the only extra credit you're going to have, or are you going to?
I don't know. No. that? Where's that? Okay, we're now going to start thinking about what happens when we, excuse me. We've been talking about probabilities of events. We've been talking about random variables, in particular random variables that come from drawing tickets out of a box at random and looking at the numbers on the tickets that we get. And we want to start looking at what long-run regularities there are in order to be able to use these box models to draw inferences about the world. One of the most fundamental notions that's applied to random variables is the expected value. And this chapter is about that, but in order to get there, I want to talk about the law of large numbers, which is a key concept in probability. So let me write this with chalk because it's easier to talk it through. So let's suppose that we have independent trials that have the same probability of success. So we can imagine tossing a coin repeatedly, really vigorously, in such a way that whether the coin landed heads each time is independent of the other times that we toss the coin. Okay? So n is the number of times I toss the coin. And p, if the coin is fair, we're sort of by definition, what we mean is the chance that the coin lands heads is 50%. Okay? Now, suppose we look at the difference between the number of heads. Boy, that's really illegible. Okay, so this is the number of heads we get in this many independent tosses of the coin. Okay, so this is a random variable. The number of heads you get in a certain number of tosses is random. Okay, so this ratio is random. It depends on what actually happens. And suppose we look at the difference between that and 50%, which is the probability that the coin lands heads in a single toss. By definition, we're talking about a pure coin. So this is kind of rarely going to be exactly equal to 50%. Yes? Just every once in a while it might happen. But what tends to happen is that let's look at the difference between the empirical fraction of successes, the empirical fraction of heads, and the probability of success, the probability of heads. And let's look at, so this thing could be big, it could be small, right? Could so happen that the fraction of heads in 17 tosses is 90%. And so 90% minus 50% is a big number. It's 40%, right? It could happen that this is really small. It could happen that the fraction of heads in 20 tosses is exactly 50%. This number is 0. All right? So this difference is random. Right? It depends on what this is, and this is random. Right? Let's ask, though, what's the chance that this difference is less than some positive number epsilon? So we're going to look at the probability that the difference between the fraction of successes and the theoretical probability of success is less than epsilon. And the law of large numbers says that this probability goes to 1 as the number of tosses goes to infinity. So the more trials you have, the more likely it is that the fraction of successes you see is arbitrarily close to the probability of success. Okay, so this is true for any fixed positive number epsilon. So we have some epsilon greater than 0. So for any fixed epsilon greater than 0, the chance that the theoretical probability differs from the empirical fraction of successes by less than that threshold value epsilon gets bigger and bigger and bigger the more trials you have. Okay, this is the law of large numbers. All right, everybody remembers what a limit is? Yep, okay. So this is a funny notion of a limit because it's a limit of a probability. It's still possible that the fraction of successes differs from the probability of success by more than epsilon. Right? It can still happen that you toss a coin 1,000,000 times, you get heads 1,000,000 times. it's just very, very, very unlikely. Yep. Okay, so the chance that these things differ by very much gets really, really small the more trials you have. The chance that the difference is really small gets big the more trials you have. You have independent trials, same probability P of success in each trial. Okay, so here it is. The difference in the fraction of successes in n trials differs from the probability of success by less than any positive tolerance E. That goes to 100% as the number of trials increases. Okay? But what does this mean about drawing tickets out of a box? Okay, so let's suppose I have 5 tickets in a box, and I draw a ticket from the box, one ticket from the box with replacement over and over and over and over again. Okay? The law of large numbers says I'm going to get the ticket. What's the probability that I get the ticket labeled A? In each draw, it's 1/5, right? So probability that I get the ticket right, it's 20% in each draw. Okay. So the law of large numbers says that as I draw from the box more and more and more and more times, the fraction of the time that I get the ticket labeled A is increasingly likely to be close, arbitrarily close to 1/5. I won't get it exactly 1/5 of the time, but the more times I draw, the greater the probability is that it's going to be arbitrarily close to 1/5. So if I drew from this box a zillion times, I would see the ticket labeled A about 20% of the time. I would see the ticket labeled B about 20% of the time. I would see the ticket labeled C about 20% of the time, et cetera. Yes? Okay. With high probability, right? It's not guaranteed to see it exactly 20% of the time, but I'm very likely to see it nearly 20% of the time. Okay, so what would happen if I added up the numbers on all the tickets that I saw in a very, very, very large number of draws from the box and took the average? If I take all those results, I draw from the box n times where n is really, really big, and I average what I see in those zillion draws from the box. Well, I would have some random list of labels, like I might get A, E, D, D, B, C, B, etc. So there's going to be some string of labels that I get as I draw from this thing repeatedly. And they're going to be a random number of each label in a random order, so forth and so on. But if I go through and I have n of these in all, then of those n, with high probability, the number of A's is going to be about n divided by 5, right? And the number of B's is going to be about n divided by 5. And the number of C's is going to be about n divided by 5, right? So the average of this whole list of repeated tickets is going to be about, I'm going to see A about n over 5 times, B about n over 5 times, et cetera. If I average them, what am I going to get? I'm going to get something like A plus B plus C plus D plus E over 5, approximately. Right? Each of them is going to occur about the same number of times in the n trials. Yes? I see them each about 1/5 of the time. Okay? All right. This number is the expected value of a draw from this box. The frequency interpretation is if I did the experiment over and over and over and over again, the probability that the average of the draws would differ from this number by more than a little bit gets really, really, really small. That is, the probability that the average of the draws is close to this number gets really, really big, approaches 100% as the number of draws gets big. Okay? Good time to ask questions if I'm confusing you. All right, let me back up because we have a little applet to show the law of large numbers here. Just shrink this down a little bit. Okay, what is this plot? This is looking at the difference between, this is simulating a toss of a coin, 50% chance of heads, and it's looking at the difference between the observed fraction of heads and the probability of heads. In this case, it's 800 trials. So what tends to happen as the number of trials gets bigger and bigger is that the difference settles down to 0. So initially, for a small number of trials, there's a pretty good chance that the theoretical chance of success and the empirical rate of success is going to differ by a lot. But as the number of trials gets bigger and bigger and bigger, the probability that they differ by very much gets smaller and smaller. Let's do another. Okay, so now here's the story for a coin that has an 11.6% chance of heads, and we're taking the difference between the observed number of the observed percentage of heads and 11.6%, the theoretical probability of heads. And again, it wanders around a while, but eventually this kind of settles down and gets very close to 0. Okay, so this is the difference between the percentage of heads and the probability of heads for this biased coin that has an 11.6% chance of heads. What happens if instead of looking at the difference between the percentage and 11.6, we look at the difference between the number of successes and 11.6% of the number of trials? Okay. Law of large numbers doesn't say that that gets small. All right, so I just toggled this. So now instead of plotting the difference between the percentage of successes and 11.6% of the number of trials, sorry, and 11.6%, I'm plotting the difference between the number of successes and 11.6% of the number of trials. This tends to actually grow the more trials you have. So the difference between the number of successes and the probability times the number of trials tends to get big. The difference between the fraction of successes and the probability of success tends to get small. Okay? How can those things simultaneously be true? Okay, here it is for an example for a fair coin. So it starts off, this is the difference between the number of successes and 50% of the number of trials. And it just wanders off. But if we look at the difference between the percentage of successes and 50%, it tends to get small. What's the relationship between the number of successes and the percentage of successes? Okay, so the number of successes tends to grow, but the probability of success times the number of trials also tends to grow. So we're comparing two things that are growing. But just mathematically, percentage of successes right? So that's the relationship between percentage of successes and number of successes, right? They're related through the number of trials. Okay, so suppose if the number of success, if the difference between the number of successes and p times the number of trials grows at the rate of n, the number of trials, or faster, then the percentage of successes wouldn't get closer to the percentage, to the probability of success. But if the number of successes, the difference between the number of successes and p times the number of trials grows slower than the number of trials, when you divide by the number of trials, that difference is going to get closer and closer to 0. So in fact, what happens is that the difference between the number of successes and the number of trials times the probability of success tends to grow like the square root of the number of trials. Okay, it grows slower than the number of trials. So when you divide it by the number of trials, it ends up getting smaller and smaller. So even though it grows slower than the number of trials. When you divide by the number of trials, the result gets smaller and smaller. Does this make sense to people? If I have something that looks like a constant times the square root of n, and I divide that by n, what happens is n gets big. This is constant over the square root of n. This gets small as n gets big. Okay? So even though this is growing, it's not growing as quickly as that is. And as a result, when you divide it by n, it gets smaller and smaller. That's what's going on here. The difference between the number of successes and 50% times the number of trials tends to grow. It tends to grow at the rate of the square root of n. But when you divide it by n to look at the difference between the fraction of successes and the probability of success, that tends to shrink at the rate of the square root of n. Is that okay? All right. Okay, so we were talking about, is this, any questions about this at the moment? Okay, this applet we saw fairly recently when we were drawing from a box of tickets where the tickets were labeled 0 and 1. Here we have 4 numbers in the box, 0, 1, 1, and 4. Right? Now, each time I draw from the box, if I draw a sample of size 1, I'm equally likely to get any of those 4 tickets. Right? There's a 25% chance of getting any one of the 4. If I draw one sample over and over and over and over and over again, I'm going to get the ticket labeled 0 about a quarter of the time. I'm going to get a ticket labeled 1 about half the time, because I'll get that one about a quarter of the time and that one about a quarter of the time. And I'll get the ticket labeled 4 about a quarter of the time. Right? So if I just did this experiment, where here, okay, so that time I got a ticket labeled 1. That time I got the ticket labeled 4. That time I got the ticket labeled 4 again. Another ticket labeled 1. Another ticket labeled 1, ticket labeled 0, etc. Right? We could just do this. Now, we could speed it up to take, let's say, 1,000 samples to just see what happens if we do this many, many, many times. Okay, we've now taken 10,000 samples of size 1 from this box of numbers. And what we would expect to see is that the area of this bin should be about 25%. The area of this bin should be about 50%. The area of that bin should be about 25%. Right? So we can actually check it from 0 to... Okay, it turned out to be 25.4% in those 10,000 trials. Okay? If we did it more, it would be likely to be even closer to 25%. We'll keep going. Yes? All right. What's the average of the values that we saw in those 10,000 draws? That's this line, mean of values. The average was 1.497. if we had seen the ticket labeled 0 exactly a quarter of the time, a ticket labeled 1 exactly half the time, and a ticket labeled 4 exactly a quarter of the time, what would that average have been? So 1.5, right? 1.5. So we've got 0 times a quarter plus 1 times a half plus 4 times a quarter. Okay, 1.5. The expected value of a draw from this box is 1.5. So if we imagine doing the experiment longer and more draws of size 1, then we would have closer and closer and closer to a quarter of the numbers in that list would be 0, closer and closer to a half of the numbers would be 1, closer and closer to a quarter would be 4, with high probability, right? Not guaranteed, but with increasingly high probability. And so when we average the list, we would have the average of a list that was a quarter zeros, a half ones, and a quarter fours. The average of that list would be 1.5. Make sense? Okay, that's the expected value. Notice, the expected value is 1.5, and yet you would be shocked to draw a ticket labeled 1.5 from this box. Yes? There are no tickets labeled 1.5 in the box. Expected value is a term of art. It is not what you expect to see. It is the long-run average of what you get if you do things over and over again. It doesn't have to be a possible value to be the expected value. All good? Okay. So, in general, how do we define the expected value of a discrete random variable? If we know its probability distribution, then if you imagine what happens when you draw over and over and over again, the frequency with which I get a particular value is going to approach, in high probability, the probability of getting that value. So in this case, this is supposed to be the probability distribution of the sum of 2 draws from that box of tickets that we were just looking at. So let's verify that this is right. So I'm going to draw twice from that box of tickets and calculate the sum of the 2 draws. Then I'm going to draw twice from that box of ticket and count the sum of the 2 calculate the sum of the 2 draws. I can do that over and over again. So I have a new experiment. The experiment is not drawing a sample of size 1. It's drawing a sample of size 2. But I'm going to repeat that experiment many, many, many times and look at the values that I get. And I'm interested in what's the average outcome for that experiment, the long-run average outcome. So what's the probability that the sum of 2 draws is equal to 0? Well, how does the sum of 2 draws end up being 0? I've got to get a 0 on the first draw and a 0 on the second draw. The 2 draws are independent. I'm drawing with replacement. So the chance I get a 0 on the first draw is a quarter. The chance I get a 0 on the second draw, given that I got a 0 on the first draw, is also a quarter because they're independent. So the probability that I get a 0 on both is a quarter times a quarter, or 1/16. Right? Okay. What's the chance that I get a 1 as the sum of the draws? What's the chance the sum of the 2 draws is 1? Well, I can either get a 0 and a 1 or a 1 and a 0. Right? I have 2 possibilities. Those are disjoint, right? If I get a 0 on the first draw and a 1 on the second, I didn't get a 1 on the first draw and a 0 on the second. Did I say that right? Okay, so I can find the probability that the sum is 1 by finding the probabilities of those 2 possibilities and adding them together because they're disjoint and exhaustive. They're a partition of the event that I get a 1 as the sum of the 2 draws. So what's the chance I get a 1 and then a 0? Well, there's a 50% chance I get a 1 because there's 2 1s in the box. And then given that I get a 1, there's a 25% chance that I get a 0 on the second draw because the draws are independent and there's 25% zeros in the box. So I get 0.5 times a quarter is an 1/8, right? And then the other way around, what's the chance I first get a 0 and then get a 1? I've got a quarter times a half, which is another 1/8. So I have an 1/8 plus an 1/8 is a quarter, is the probability that the sum is equal to 1. Okay? What are the ways of getting 2? You can get a 1 and a 1, a 0 and a 2, or a 2 and a 0. Right? 1 and 1 is a half times a half is a quarter. 0 and 2 is a quarter times a quarter is a 16th. 2 and 0 is a quarter times a quarter is a 16th. So I get 2/16, which is an 1/8, plus a quarter is 3/8. Did I do that right? No, I did leave something out? Oh, I'm sorry, there's no 2 in the box. Okay, that would explain it. Yeah, I was thinking that there was a 2 in the box. Keep your eyes on the box. Okay, yeah, so there's only, you can, to get 2, you have to get a 1 and a 1. That's the only way you can do it. And the chance you get a 1 and a 1 is a half times a half is a quarter. All right, okay. So we can work this out and find the whole probability distribution for the sum of 2 draws from this box. These are the possible values. Those are the only sums you can get. And these are the probabilities of these values. Well, if we repeated this experiment of drawing twice from the box over and over and over again, each time adding the results, we would get 8 about a 16th of the time. We would get 5 about a quarter of the time, etc. The expected value of this is going to be 0 times a 16th, plus 1 times a quarter, plus 2 times a quarter, plus 4 times an eighth, 5 times a quarter, 8 times a 16th, right? Because we'll see each of these values about that often. Okay, so it turns out that the expected value is 3, which is twice what the expected value was for 1 draw from the box. Okay, that turns out to be true in great generality. The expected value of n draw, the sum of n draws from a box is equal to n times the expected value of 1 draw from the box. The expected value of 1 draw from the box is the average of the numbers on the tickets, where you take into account repeats. So in this case, it's the average of 0, 1, 1, and 4. Right? That turned out to be 1.5. The average of 37 draws from this box, the expected value of the sum of 37 draws from this box would be 37 times 1.5. Okay? So the experiment is pull 37 tickets out of the box with replacement, add them. Do it again. Pull 37 tickets out of the box with replacement, add them. You get number each time. Imagine doing that over and over and over again an enormous number of times. Each experiment consists of pulling 37 tickets out of the box with replacement. What would the average of that list be? Well, with increasingly high probability, the average of that list would be increasingly close to 37 times 1.5. 37 times 1.5 is the expected value. Okay. In general, the expected value of a discrete random variable is a weighted sum of the possible values the variable takes. So we have a random variable x. It can take values x1, x2, x3. Right? In this case, we're talking about a single draw. The random variable was, what number do you see on the ticket? What are the possible values? The possible values were 0, 1, 1, and 4. Right? So these are the possible values of the random variable. What's the expected value? Well, it's a weighted sum of the possible values where the weights are the probabilities that the random variable takes that value. Okay? Because the random variable is going to take this value about that often. And it's going to take this value about that often in repeated trials. Okay. I'm just going to state without proof the thing that I said a moment ago, which is if I draw n times from a box of tickets and I look at the sum of the, I draw n times at random from the box of tickets and add the values in the tickets that I see. The expected value of that is n times the average of the labels on the tickets in the box. If I draw once, the expected value is the average. If I draw twice, it's twice the average, etc. Right? It turns out that this is true even if I draw without replacement from the box. Of course, if I draw without replacement from the box, I can't pull more tickets out than are in the box in the first place, so little n needs to be less than the number of tickets in the box. But it works out that the expected value of the sum of n draws from a box of numbered tickets is n times the average of the labels on the tickets, the numbers on the tickets. Okay? All right, let's look at some special cases. We were talking about 0, 1 boxes for the last couple of lectures. What is the average of the numbers in a 0, 1 box? So if I have a box that has capital N tickets in all, and a fraction P of them are labeled 1, and a fraction 1 minus P of them are labeled 0, then what's the average of the labels? Well, I have N times P 1s plus N times 1 minus P times 0, right? That's the sum of all the labels. And I have N tickets in all, right? Okay, the average of the labels on all the tickets in the box is just P. Okay. Now, remember that the binomial distribution is the distribution of the sum of little n draws with replacement from a box of tickets like this. Yes?
What is the difference between the average of labels and expected value of a set?
So the question is, what's the difference between the average of the labels and the expected value? So the labels are just some particular list of numbers, okay? And we can calculate the average of that list. It turns out that what the expected value, what's the expected value defined to be? It's defined to be the sum of, so we have a random variable now, which is what do you get when you pull a ticket at random from the box. The random variable is the number on that ticket. The expected value is the sum of the possible numbers you can get on the ticket times the probabilities of the numbers that you get when you draw. So expected value is a concept that applies to random variables. Average is a number that applies to lists. They're analogous. The expected value of a random variable is a weighted sum of its possible values. It turns out that numerically, the expected value of the number on a draw from this box, a draw at random from this box, is equal to the average of the numbers on the tickets in the box. So that's a result rather than a definition. Right? The definition is, it's really defined to be the sum of the possible values each times the probability of those values for a random variable. That's the definition. And then it turns out that that's exactly equal to the average of the labels on the tickets in the box if the experiment is pull a ticket at random from the box.
And so they're always equal to each other?
The expected value of the number that you get when you draw a ticket at random from a box is always equal to the average of the labels on the tickets in the box. And indeed, the expected value of the sum of n draws, the sum of the labels on n draws from the box is equal to n times the average of the label of the tickets in the box. And that's true whether you're drawing with or without replacement. Again, it's a result. It's not a definition. Okay. So remember, binomial distribution is like the number of tickets labeled 1 we get if we draw with replacement from this box little n times. And we count how many tickets labeled 1 we get. And I've mentioned a couple of times that counting the number of tickets you get that are labeled 1 is the same as adding the labels on the tickets that you get. Because when you add a string of zeros and ones, what do you get? How many ones there were. Right? The zeros don't contribute anything. The ones each contribute 1. It's just counting how many ones there are. Okay, so the probability distribution of the number of tickets labeled 1 you get in little n draws with replacement from this box is, so that probability distribution is binomial with parameters little n and little p, right? So let's calculate, we're going to look at the probability, we're going to look at the expected value of a binomial distribution 2 different ways. One is starting with a definition, and the other is using the fact that we have a box model that leads to the binomial distribution. So if we wanted to start with a definition that says this, the expected value is defined to be the sum of the possible values times the probabilities of those values, then what piece of math do we need to write down to calculate the expected value of a binomial distribution? So if we have a binomial distribution with parameters n and p. So we have a random variable that has a binomial distribution with parameters n and p. But let me back up a couple of steps. The expected value of a random variable just depends on its probability distribution, right? Because it's just a weighted value, a weighted sum of the possible values times the probabilities of those values. Okay? It doesn't depend on the outcome of some experiment. It just depends on the probability distribution. So there's no, we can talk about the expected value of a probability distribution or the expected value of a random variable. It makes sense because the expected value of a random variable just depends on its probability distribution. Okay, so suppose we have a random variable that has a binomial distribution with parameters n and p. So that is, it's like the sum of the labels on little n draws with replacement from that 0, 1 box. Okay, so what's the expected value? It would be the sum of the possible values times the probabilities of those values. What are the possible values? When we draw n times and add the results on the tickets, little n times, what are the possible values we can see from the sum? We might get a ticket labeled 0 every time, right? Or we might get a ticket labeled 1 every time. The possible values range from there's 0, 1, 2, 3, etc., on up to n. Those are the possible values for the sum of the n draws. So let's say this is the sum from j equals 0 to n. J is now standing for the possible values, okay, of j. That is the possible value. That's taking the role of x sub something, right? So it might be 0. What's the probability that it's 0? Right? This is the binomial distribution. So we have j is the possible value, and then this is the probability that we get j successes, that we get j tickets labeled 1 when we draw from the box. We have to get one of the tickets labeled 1, j times. Each time there's probability p that happens. They're independent. So we multiply, and we also have to get a ticket labeled 0 n minus j times. And there are n choose j different ways we can do that in the n trials. Right? This should ring a bell by now, this piece. Okay? So we could do this sum, and it would take us the rest of the lecture. Okay? Or we could use the fact that a binomial is, what has a binomial distribution? Well, little n draws with replacement from that box of tickets. If you take the sum of the draws, sum of little n draws, okay. And what do we know about the expected value of the sum of n draws with or without replacement from a box of numbered tickets? We know that it's little n times the average of the values on the tickets. Yes? And we know that the average on the values of the tickets in this case is P. So this whole thing is just going to be equal to n times P. If we work it out. Yes?
J in front of the binomial distribution is the value on the ticket, right?
Right, so that J is like taking this roll. So this is like 0 times the probability that you get 0, 1 times the probability you get 1, 2 times the probability you get 2, on up to n times the probability that you get n tickets labeled 1. Okay.
So where did the J?
Where did, sorry?
The J?
Wh- Why what?
How did they like disappear?
Why did it disappear? Well, we're summing over it, all of its possible values. This is a dummy variable that's just inside the sum. We have, this sum has n plus 1 terms. One of those terms, j, is 0. We get 0 times something. That's not going to contribute anything. Another term, this is 1. So we'll get 1 times n choose 1, which is n, times p to the 1, times 1 minus p to the n minus 1. That's the next term. Then j is going to be 2. We'll get 2 times n choose 2, et cetera. Right? We'll sum all that up. If we did that, the answer would be n times p. Okay? So using our notion that the expected value of the sum of n draws from a box of numbered tickets is just n times the average of the numbers on the tickets in the box, we can shortcut a very difficult calculation and just write down the answer. Okay? So far, so good? Question? The average of the numbers on the tickets in the box is little p. We're drawing little n times from the box because we're asking about a binomial distribution that has parameters n and p. So it's like the sum of the tickets we get on little n draws from a box where there's a fraction little p of tickets labeled 1 in the box and the rest are labeled 0. Okay, so we've just seen that the expected value of a random variable that has a binomial distribution with parameters n and p is just n times p. Sometimes when we draw from the box little n times, we're not going to get any tickets labeled 1. Sometimes we're going to get 1 ticket labeled 1. Sometimes we're going to get 17. Sometimes we're going to get n. Right? On average, how many tickets labeled 1 do we get when we draw little n times from the box? On average, we get n times p. That might not be an integer, right? It might not be a possible number of tickets. It's on average what would happen in the long run. We all together? Okay, I asserted without proof that it doesn't make any difference whether you draw with replacement or without replacement. The expected value is still the number of draws times the average of the numbers on the tickets in the box. Okay? We have another random variable that's like drawing without replacement from this box of tickets. What distribution is that? If I draw little n times without replacement from a box of 0, from a 0, 1 box. Hypergeometric. Okay. So for hypergeometric, I would call this number G, right? G is the number of tickets in the box that are labeled 1. There's n tickets in the box in all. Okay. What is the average of the labels on the tickets in the box here? It's still P, but I can write this in terms of the parameters of the hypergeometric. What's the fraction in terms of G and N? What is P? Yeah. Number of tickets labeled 1 divided by the total number of tickets there are. Okay. So let's suppose that I draw at random without replacement little n times from this box and add the numbers on the tickets that I see. That's like counting how many 1s I get. Right? How many tickets labeled 1 do I get in that sample without replacement? what's the expected value of that sum? Yeah, it would be little n times big G over big N, provided little n is less than big N. Can't pull more tickets out of the box than there are in the box if you're sampling without replacement. If I wanted to do that from the definition of the expected value, what would I have to calculate? So suppose I have a hypergeometric distribution with parameters n, g, and little n. Then how would I calculate its expected value if I didn't know this shortcut? Yeah, I'd be doing some sum that involves taking j times the probability that the random variable is equal to j. What's the probability that the random variable is equal to j? We have this sort of max and min thing. We have to worry about the possible values. But for a feasible term, what does it look like? From the good tickets, I need to choose j. From the tickets labeled 0, I need to choose n minus j. And from all the tickets, I need to choose n. Right? So I would be looking at the sum of j times this thing, this combinatorial ratio thing, and adding the terms for all the possible values of j. Possible values of j are going to depend on how many tickets I pull out of the box, et cetera. It's going to be integers, but it might not start at 0, depending on the sample size. Okay, so this mess is going to end up reducing to little n times big G over big N, which is the analog of little n times little p for the binomial. The expected value for the binomial is the same as the expected value for the hypergeometric. It is the number of draws times the fraction of ones there are in the box. Okay. So far, so good? Okay. The expected value satisfies some algebraic identities that make it easier to calculate expected values in complicated situations by reducing it to simpler problems. So first of all, the expected value of a constant is just that constant. If I have an experiment that no matter what happens returns the value 1, then in the long run, the average value I get is going to be 1. Right? Okay, the expected value of a constant is just a constant. The expected value of a sum of random variables is always the sum of their expected values. Okay? This is incredibly powerful. This little linear, this additivity property. Okay? And then the final thing that's extremely useful is the expected value of a constant times a random variable is that constant times the expected value. Okay? So if I pull people at random from the room, one person at random, and calculate their height in meters, and I ask what's the expected height in meters of someone drawn at random from the room, and I say, okay, what's the expected value in inches instead of meters? It's just going to be the conversion between meters and inches times the expected value in meters. It scales. Okay. All right, so we're going to use this last thing, that the expected value of a constant times a random variable is a constant times the expected value of the random variable, to figure out the expected value of the sample mean from what we know about the expected value of the sample sum. Okay, so we've been talking about pulling tickets at random
What?
What? Okay, we've been talking about pulling tickets at random and adding the values on the tickets. That's the sample sum of n draws from the box. Suppose we pull little n tickets at random, and then instead of adding them, we average them. That's the sample mean. Okay? What's the expected value of the sample mean? So the sample mean of n tickets drawn at random from a box is equal to sample sum of the n tickets divided by n, right? You add them together and you divide by how many you have. Okay? So that is, you can write it as 1 over n times the sample sum. Yes? That's a constant times the sample sum. So the expected value of the sample mean is that constant times the expected value of the sample sum. Right? That's this rule. Expected value of a constant times a random variable is a constant times the expected value. So the expected value of 1 over n times the sample sum is 1 over n times the expected value of the sample sum. Yes? Can I re-explain it a different way? What I mean by sample mean? Okay, so we've been talking about say a 0, 1 box. Okay, and suppose I pull 5 tickets at random out of the box. I might get the tickets 0, 1, 1, 0, 1. Okay? The sample sum is 0 plus 1 plus 1 plus 0 plus 1 is 3. The sample mean is 0 plus 1 plus 1 plus 0 plus 1 divided by 5. Okay? Okay, so suppose that I pull 5 tickets at random out of this box with replacement. Then the number of tickets labeled 1 I get is going to be random. On average, the fraction of tickets labeled 1 in the sample is going to be little p. The sum of the labels and the tickets I get is going to be little n times little p, on average. That's the expected value. So the expected value of the sample sum gosh, my handwriting is just so terrible. I'm so sorry. So the expected value of the sample sum is going to be n times p. The expected value of the sample mean is equal to 1 over n times the expected value of the sample sum. Which is 1 over n times np, which is p. So if the expected value of the sample sum of n tickets drawn at random from a box is n times the average of the number of tickets, n times the average of the numbers on the labels, the tickets in the box. Then once I take n times that average and divide it by n, I get back the average. The expected value of the sample mean is the mean of the numbers on the tickets in the box. So the expected value of the sample mean is the population mean, population of tickets in the box. Does this make sense? Okay. And that's true whether I'm drawing with replacement or without replacement from the box. The expected value of the sample mean is still the population mean, still the mean of the numbers on all the tickets in the box. That's going to turn out to be very important. The sample mean in general is you add the labels on the things that you get in your sample, you divide by how many there were. In the special case that you're drawing from a 0-1 box, the sample mean is the percentage of ones in the sample. So the sample percentage is a special case of the sample mean when you're drawing from a 0-1 box. All you can get are zeros and ones. If the things are red or green, and you're interested in the fraction of red ones, then the number of red ones divided by the sample size is the percentage of red ones. Right? So the sample percentage is a special case of the sample mean. All right, so the expected value of the sample mean of n random draws with or without replacement for a box of numbered tickets is the average of the numbers on the tickets in the box. Special case of that is if the tickets are all labeled just 0 or 1, then the expected value is the percentage of the tickets in the box labeled 1. So far, so good? Okay. All right. What motivated so much of probability in the first place is gambling, right? How do you figure out what's a fair bet, what's not a fair bet? How should you place your money? So expected value is intimately tied to whether a bet is fair or not. The difference between your the expected amount by which the expected amount of money from each dollar that you lose in repeated play is called the house edge. A bet is fair if the house edge is 0. That is, if on average you would expect to break even in the long run. If on average you expect to lose money in the long run, the house has an edge. And in all casino games, there is a house edge. If you play long enough, you will lose all your money. I mean, that's just how it's built. I mean, unless you're cheating, right? That's okay. All right, so let's look at what the house edge is for a bet on red in roulette. Oh, the way a roulette wheel works is there's a wheel and it has 38 positions. There are there are 36. So that's 18 of them are red, 18 of them are black, 2 of them are green, if I'm remembering correctly. Okay, somebody go to Vegas or okay. Okay, so the payoff for winning a bet on red is sort of break even. That you sort of you double your money. You get your money back and you get your dollar back in another dollar if it lands on red. Okay, otherwise you lose your money. Yes? So if the chance that the ball landed on red was 50%, then there would be no house edge. But the chance that the ball lands on red is less than 50%. Okay, the chance the ball lands on red is 18 out of 38 rather than 19 out of 38. We break even if it were 19, but only 18 of 38 positions are red. So out of each dollar you bet, you expect to lose a little more than a nickel. Okay, and in the long run, if you keep playing over and over and over and over again, with very, very high probability, your losses are going to increase until you have no more money. Okay. What's a fair bet? A fair bet is one where the expected value payoff, the expected amount of money you get back is 0 after you account for how much money you have to ante up to play. Okay. your expected payoff is positive, the bet favors you. If the expected payoff is negative, the bet favors somebody, whoever you're playing against. The house. Okay. Let's go over some of this stuff and hint at how you get some of these results. So we already figured out that the expected value of a binomial random variable with parameters n and p is n times p. It's like, it is the sample sum of the numbers on the tickets that you get if you draw independently with replacement from a 0, 1 box that has a fraction p of tickets labeled 1, and you draw a little n times. Okay? Expected value of a geometric random variable. What's a geometric? Okay, so you're drawing from a 0, 1 box with replacement independently until the first time you see a ticket labeled 1. All right. Why does it make sense for the expected value to be 1 over p? So I'll give you a heuristic, and then I'll show you the proof briefly because you really don't want to see it. Heuristic is you get, if there's p tickets labeled 1, then every time you draw, you get sort of, there's p successes per draw. Does that make sense? You get sort of a fraction p tickets labeled 1 per draw on average. And so if you get p successes per draw, then how many draws per success are there? 1 over p, loosely speaking. So on average, how many times would you have to draw to get 1 success? On average, 1 over p. That's a loose heuristic. It's not completely accurate, but the proof that that's the expected value is a little longer. So you don't want to know that. You don't have to know that. Okay, but let's assume that we take this now as given, that the expected value of a geometric random variable with parameter p is 1 over p. From that, we can actually derive the fact that the expected value of a negative binomial random variable with parameters p and r is r over p. So let's reason that out, because this reasoning is actually helpful. Right. Remind me, what kind of thing has a negative binomial distribution? Okay, so we've got a 0, 1 box, right? Fraction p tickets labeled 1 in the box. We draw with replacement until the rth time we get a ticket labeled 1. Okay. Let's think of that as occurring in stages. We draw until the first time we get a ticket labeled 1. Then we draw until the next time we get a ticket labeled 1. Then we draw until the next time we get a ticket labeled 1, until we've done that r times. Okay? What's the distribution of the number of times I have to draw until I get the first ticket labeled 1? It's geometric, right? Now, starting there, what's the distribution of the number of times I have to draw until I get another ticket labeled 1? It's again geometric, right? I'm waiting from then until the first time I get a ticket labeled 1. And then once that's happened, I'm waiting from there until the first time I get a ticket labeled 1. And I have to do that a total of r times. So I could actually write a negative binomial random variable as the sum of r geometric random variables. So if we have x1, x2, so forth, on up to xr, if these all independent random variables with the geometric distribution with parameter p, then if we define x to be x1 plus xr, the distribution of x is negative binomial with parameters r and p. Okay? I wait until the first time, and then I wait until the second time, and then I wait until the third time. Each time I'm drawing with replacement from the same box of tickets, same fraction p of tickets labeled 1. Everything is independent, right? So I can think of waiting for the 7th ticket labeled 1 as waiting for the first ticket labeled 1 and then starting over, and waiting for the first ticket labeled 1 and then starting over, and doing that 7 times. Okay, so the distribution of the sum of r independent geometrics is a negative binomial with parameters r and p. Okay, now we have that little rule that says the expected value of a sum is the sum of the expected values. What's the expected value of this geometric random variable? We've sort of said it's 1 over p without proving it. Yeah? The expected value of this one is 1 over p, et cetera, and the expected value of this one is 1 over p. So what's the expected value of their sum? R over p. Expected value of their sum is the sum of their expected values. 1 over p, 1 over p, 1 over p, 1 over p. That adds up to r over p. So knowing this, it's easy to prove this. Okay. Hypergeometric, we already did. Again, it's draws, in this case, without replacement from a box of numbered tickets. The average of the tickets in the box, the labels on the tickets in the box, is g over n. That's the fraction of tickets labeled 1 in the box. In general, if we draw little n times with or without replacement from a box of numbered tickets and add the results that we see, that sample sum, the expected value of the sample sum is n times the average of labels on the tickets in the box. The expected value of the sample mean is this divided by n, which is just the average of the labels on the tickets in the box. Of course, if we're drawing without replacement, we can't draw more times than there are tickets in the box. All right, let's do an example. Okay, so we've got a loaded die. We're going to roll it 6 times, and we want to know what's the expected number of spots that show in 6 rolls of this die. So we can think of each roll as giving us a random number of spots, right? And the total number of spots we see in 6 rolls is the sum of 6 random variables that all have the same distribution, right? Each time you roll it, you get a new number. So each draw, each experiment, each time we roll the die, it's like drawing from a box of numbered tickets where there's 0.028 times the number of tickets in the box are labeled 1, 0.305 times n of the tickets in the box are labeled 6, and then 2, 3, 4, 5. There's each of these has a 6th times n. My handwriting, I'm so sorry. Do this a little better here. Give myself more space to start with. 4, a 6th times n, and 5 has a 6th times n. Okay, everybody has it on a die. The sum of the spots on the top and bottom add up to 7. Right? Opposite faces, they add to 7, which is why I've tweaked 1 and 6 here, because they're on opposite sides. Okay. All right, so if I draw from this box once, what's the expected value of one draw from this box? It's going to be the average of the numbers on the tickets in the box. So 0.028 n of them are labeled 1. 0.305 n of them are labeled 6, etc. If I wrote them all out, I need to sort of put it over a common denominator, but if I wrote them all out and then added them up and divided by n, what would I get? 1 times 0.028 plus 6 times 0.305 plus 2 times a sixth plus 3 times a sixth, etc., right? That would be the average of the labels on the capital N tickets there are in this box, right? There aren't the same number of tickets with every number. These have the same number. These differ from each other and from those, right? Okay, so if I do this sum, that's the expected value of one draw from the box. What's the expected value of 6 draws from the box? 6 times whatever that gives us. Okay, the sum of the numbers we get in 6 draws from the box. And that's true whether we do it with or without replacement. We've got like 2 minutes. Let's just hint at the beginning of exercise 18.7. I'm going to roll a fair die. If the die shows 3 spots, I'm then going to roll 3 more dice. If the die shows 1 spot, I'm going to roll 1 more die. Okay, I'm going to roll as many dice as show the first time that I roll. Does this make sense? I'm rolling a random number of dice. Right? What's the expected value of the total number of spots that are rolled in the second part of the experiment, not including the one that figured out how many dice you're going to roll in the second part of the experiment? How do I do this? Well, the first roll might give me 1 spot. Okay, what's the chance it gives me 1 spot? A sixth. Okay. If it does give me 1 spot, then I'm going to roll 1 die. Right? If I roll 1 die, I could get any number of spots between 1 and 6. There's probability a 6 that I get 1 spot, probability a 6 that I get 2 spots, etc. It's like one draw from a box of numbered tickets numbered 1 through 6. Okay? So if I knew that I were only rolling 1 die, then the expected value of what I would get would be 1 plus 2 plus 3 plus 4 plus 5 plus 6 divided by 6, which is 3.5. Okay, remember opposite faces sum to 7. So, okay. Okay. Suppose that I get 2 spots. Probability of that is a sixth. If indeed I got 2 spots, I'd be rolling 2 dice. What's the expected number of spots that I would see if I did that? Okay, so it'd be 2 times 3.5 is 7, right? Etc. Okay, so what's the expected number of spots that show on the die or dice that are rolled the second time? Well, there's a 1/6 chance of getting this, and a 1/6 chance of getting this, and a 1/6 chance of getting 10.5, and a 1/6 chance of getting blah, blah, blah. So it add these numbers and divide by 6. Right, now there's a little subtlety going here because we're conditioning on how many spots show up the first time we roll the die. If you look at the detailed solution to that, it'll make it a little bit more rigorous. Okay. All right, I should let you guys go, I think.